Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year of our consideration is 1931. Before us lies Principles of Quantum Mechanics, a seminal work by Paul Dirac. This book, a landmark in scientific thought, represented a deliberate attempt to formalize a theory that had, at the time, achieved remarkable predictive success, yet lacked a unified, consistent mathematical framework. Quantum mechanics, in its nascent state, struggled with the reconciliation of its two primary formulations, Heisenberg's matrix mechanics and Schrödinger's wave mechanics. These, despite their predictive power, were mathematically dissimilar, casting a shadow of ambiguity over the underlying reality they purported to describe. Dirac, a man of unwavering intellectual rigor, sought to resolve this dissonance. Dirac's ambition, as expressed within the pages of this book, was to provide a complete and self-contained exposition of quantum mechanics. He aimed to construct a system that was logically consistent and mathematically elegant, that could be applied to any quantum system. It was within this context that Dirac confronted one of the most pressing issues of the period, the need to reconcile quantum mechanics with special relativity. Dirac, a gifted theoretical physicist, understood that the existing formulations of quantum mechanics, based on the non-relativistic Schrödinger equation, were inadequate for describing particles moving at speeds comparable to that of light. This challenge became a central focus of his work. The enduring legacy of Principles of Quantum Mechanics stems, in large part, from Dirac's introduction of bra-ket notation. This innovative mathematical formalism provided a powerful tool for abstractly representing quantum states and operators. A quantum state, in Dirac's vision, could be represented by a ket vector, denoted by a symbol such as ket psi. Conversely, a bra vector, denoted bra psi, represented the dual of the state. The inner product of a bra and a ket, often denoted bra phi ket psi, represented the probability amplitude for the system to transition from the state ket psi to the state ket phi. Consider, for example, the principle of superposition. A quantum state, such as a qubit representing the spin of an electron, could simultaneously exist in multiple states. Dirac's notation elegantly expressed this. A superposition of two states, say spin up and spin down, could be written as a linear combination of the corresponding ket vectors. This notation allowed for a more general and elegant formulation of quantum mechanics, independent of specific representations, whether in position space, momentum space, or any other mathematical framework. This generality proved crucial in the subsequent development of quantum theory. The book's impact proved immediate. Physicists recognized the power of Dirac's approach. It facilitated simpler calculations and provided a deeper understanding of the underlying principles. The book's clarity, mathematical rigor, and systematic presentation transformed the way physicists approached quantum mechanics. It served as a unifying roadmap for resolving the conceptual and mathematical challenges that had plagued the early development of the theory. In understanding Dirac's achievement, it is important to acknowledge his predecessors. Heisenberg, Schrödinger and Born, among others, laid the groundwork. Heisenberg's matrix mechanics, with its emphasis on observable quantities and algebraic manipulation, and Schrödinger's wave mechanics, with its elegant description of quantum systems using wave functions, provided the initial, competing descriptions. Dirac synthesized these two approaches. He recognized that both represented different manifestations of a more fundamental, underlying structure. He used the operator formalism to present quantum mechanics in a way that was independent of any particular representation. This synthesis was a defining contribution. Consider the ongoing relevance of Dirac's work. Bra-ket notation is a staple in modern quantum mechanics textbooks and research papers. It continues to simplify complex calculations. It aids in clear conceptualization. It remains an indispensable tool for physicists and other scientists. Dirac's work offered a system of mathematical symbols that allowed physicists to avoid cumbersome coordinate systems. Dirac's work provided a uniform language. The influence of Principles of Quantum Mechanics extended beyond its immediate impact. John von Neumann, another giant in the field, was deeply influenced by Dirac's formalism and rigor. Von Neumann's Mathematical Foundations of Quantum Mechanics, published in 1932, built upon Dirac's work by providing a rigorous mathematical framework for quantum mechanics based on Hilbert space theory. This strengthened the foundations of the theory. The book became a standard reference for anyone seeking deeper understanding of the theory. In summary, Principles of Quantum Mechanics stands as a monument to rigorous thought. It synthesized disparate approaches, developed a powerful new notation, and laid the foundation for future theoretical advancements. It facilitated the subsequent development of quantum mechanics and transformed the way we think about the quantum world. Its influence extends far beyond its publication date. The work continues to resonate with physicists and scholars. Dirac's Principles of Quantum Mechanics, published in 1931, offered more than a synthesis of existing quantum theories. It presented a uniquely elegant and powerful framework that continues to shape our understanding of the quantum realm. Two concepts central to Dirac's treatment deserve particular attention: the Dirac equation and Dirac's transformation theory. The Dirac equation, conceived in 1928, sought to reconcile quantum mechanics with special relativity. The conventional Schrödinger equation, while successful in describing many quantum phenomena, treated time and space asymmetrically. This conflicted with the fundamental principle of relativity, which postulates that both are inextricably linked. Dirac's genius lay in finding a relativistic wave equation that accurately described the behavior of electrons, particles with spin described by half-int. The Dirac equation takes the form I times h bar times gamma superscript mu times d sub mu minus mc acting upon psi equals 0. Here, I represents the imaginary unit, h bar denotes the reduced Planck constant, gamma superscript mu represents the Dirac gamma matrices, d sub mu represents the four-vector derivative, m denotes the mass of the electron, c represents the speed of light, and psi represents the four-component spinor wave function. The gamma matrices are 4 by 4 matrices that satisfy a specific intercommutation relation gamma superscript nu plus gamma superscript nu. Gamma superscript mu equals 2 times eta superscript mu nu times I, where eta superscript mu nu represents the Minkowski metric tensor and I represents the 4 by 4 identity matrix. The equation's implications were profound. Solutions to the Dirac equation predicted the existence of negative energy states. Initially perplexing, these states led Dirac to propose the existence of positrons, antimatter counterparts to electrons. The positron possesses the same mass as the electron but carries a positive electrical charge. This prediction, initially met with skepticism, received experimental confirmation in 1932 when Carl Anderson discovered the positron through cosmic ray experiments. This verification revolutionized physics, solidifying the Dirac equation's place at the forefront of quantum theory and opening new avenues of research into antimatter and particle physics. Dirac's transformation theory provided a flexible language for relating different representations of quantum states. In quantum mechanics, a physical state can be described in various ways, such as its position or momentum. Dirac's transformation theory provided a means to transition seamlessly between these representations. Consider a quantum system in which the state vector can be represented in either the position basis or the momentum basis. Let psi of x represent the wave function in the position basis, and let phi of p represent the wave function in the momentum basis. The transformation theory provides a way to relate these two representations via p equals the integral of left angle p vertical line x right angle psi of x dx, where left angle p vertical line x right angle represents the transformation amplitude between the position eigenstate labeled by x and the momentum eigenstate labeled by p. Similarly, psi x equals the integral of left angle x vertical line p right angle phi of p dp, where left angle x vertical line p right angle represents the transformation amplitude between the momentum eigenstate labeled by p and the position eigenstate labeled by x. The transformation amplitudes satisfy the relation left angle x vertical line p right angle equals 1 over the square root of 2 pi h bar times e to the power of I p x over h bar. These transformations make it possible to calculate probabilities and expectation values in different bases, simplifying calculations and providing deeper insights into the underlying quantum phenomena. Such transformations are critical. For example, when calculating the scattering cross-section of a particle, one represents incoming particles in the momentum basis, then measures the resultant particles through space. Dirac also offered insight into superposition, a concept at the heart of quantum mechanics. A quantum system exists in a combination of multiple states simultaneously. Only upon measurement collapses the system into specifically one of those states. Dirac articulated this principle with exceptional clarity, emphasizing that the state of a system is described by a superposition of its possible eigenstates. A simple example of this is a superposition of spin states. An electron possessing intrinsic angular momentum or spin may either spin up or spin down along a given axis. A quantum state of an electron can exist as a combination of these two spin states, represented as psi equals a times vertical line spin up right angle plus b times vertical line spin down right angle, where and b are complex numbers representing the probability amplitudes for the electron to be in the spin up or spin down state, respectively. When a measurement of the electron spin occurs along the specified axis, the state collapses into either the spin up or spin down state, with probabilities given by the absolute square of A or the absolute square of B respectively. This principle of linear superposition is foundational to many quantum phenomena. Principles of quantum mechanics also exerted a notable influence on later developments in quantum field theory. As a complete system and textbook, scientists referred to Dirac's writing, who advanced the entire theoretical field. Richard Feynman, deeply inspired by Dirac's principle of least action found in the Lagrangian formulation of quantum mechanics, developed the path integral formulation of quantum mechanics. Julian Schwinger and Shinichiro Tomonaga relied on Dirac's relativistic quantum mechanics in their work on quantum electrodynamics, a theory describing how light and matter interact. Principles of Quantum Mechanics remains a foundational text shaping physics education and research. It provides a complete framework into the strange world of quantum mechanics. The influence of Principles of Quantum Mechanics extended beyond its immediate impact. John von Neumann, deeply influenced by Dirac's formalism and rigor, created Mathematical Foundations of Quantum Mechanics, published in 1932. This built upon Dirac's work by providing a rigorous mathematical framework for quantum mechanics based on Hilbert space theory. This strengthened the foundations of the theory and became a standard reference. Dirac's text stands as a monument to rigorous thought, facilitating the development of quantum mechanics and transforming our understanding of the quantum world. Its influence extends far beyond its publication date and continues to resonate with physicists and scholars. The Dirac equation remains very relevant in modern particle physics research, especially in exotic particle studies and the search for novel physics beyond the standard model.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.